Welcome to all of you. Now we discuss about MCQ Paper CC-8 Semester 4 2022 Real Analysis, Riemann Integration, Improper Integral and Series of Functions. Question paper 2022 question 1a. Let F maps closed interval AB to real number R be a bounded function and PQ be any two partitions on the closed interval AB. Then correct option 3, LPF less than equal to U P union QF. Now we know if P and Q are any two partitions of closed interval AB, then LPF less than equal to UQF and LQF less than equal to UPF, where F maps from the closed interval AB to real number R be a bounded function. And next theorem, if P and Q are two partitions of the closed interval AB, then P is a subset of P union Q and Q is a subset of P union Q. That is, P union Q is a refinement, actually common refinement of the partitions P and Q of both P and Q. Then LPF less than equal to LP union Q F and UP union QF less than equal to UPF, and LQF less than equal to LP union QF and UP union QF less than equal to UQF. Hence, by the first theorem, that is this, here P is a partition and P union Q is also another partition of the closed interval AB. Hence, by this first theorem, LPF less than equal to UP union QF is the correct option 3. Next question B, identify the set which is not negligible. Correct option 4, the set of points of discontinuity of functions F maps closed interval 0, 1 to R defined by fx equal to 1 if x is rational and 0 if x is irrational. Here fx, correct option for fx is a bounded function in the closed interval 0, 1. The set of points of discontinuity of fx is not a set of measured 0. That is, means f is not continuous almost everywhere in the closed interval AB, and f is not Riemann integrable in the closed interval 0, 1. Now, what is set of measured 0? This is note, this a subset S of the real number, set of real numbers R is said to be a set of measured 0 or a 0 set or negligible set or null set if for every epsilon greater than 0 there exists an almost countable family sequence In of open intervals such that S is a subset of union In and summation modulus of In is less than epsilon. Then this subset S is said to be a set of measured 0. Now, example, a finite set of in real numbers R is a set of measured 0. An enumerable subset of R is a set of measured 0. The set Q, set of all rational numbers, is a set of measured 0. The set Z, set of all integers, N, set of all natural numbers, are sets of measured 0. Every subset of a set of measured 0 is a set of measured 0. If S be an infinite bounded subset of R such that the derived set S dash of S is finite, then the set S is a set of measured 0. The necessary and sufficient condition that a bounded function f defined on the closed interval AB is Riemann integrable is that the set of all discontinuities of f in the closed interval AB is a set of measured 0. That is, f is continuous almost everywhere in the closed interval AB. Hence, the correct option is this 4. This is the set not negligible, that is not a set of measured 0, and this is the point of discontinuity for this function. Next question C. F maps closed interval AB to set real numbers R and G maps closed interval AB to real number R are bounded functions such that f into G maps from the closed interval AB to real number R is Riemann integrable on the closed interval AB, then correct option 4, f and G may not be Riemann integrable on the closed interval AB. If f and G are bounded functions on the closed interval AB such that this product fg is Riemann integrable on the closed interval AB, then f and G are not necessarily Riemann integrable on the closed interval AB. Consider the following example for this. F is a mapping from closed interval 0, 1 to R and G is a mapping from 0, 1 to closed interval 0, 1 to R be two functions defined by fx equals to -1 when x is a rational in the closed interval 0, 1 intersection rational set Q. Fx equal to 1 if x is irrational in the closed interval 0, 1, that is 0, 1 minus Q. So instead of x is, when x is rational, then fx equal to 1. Then gx equal to 1 when x is rational and gx equal to -1 when x is irrational in the closed interval 0, 1. Clearly, the product fg is mapping from 0, 1 to R and is given by fgx equal to -1, either rational or irrational. When f is rational, then fx equal to -1 and gx equal to 1. So product -1 into 1 is -1. If x is irrational, then fx is equal to 1 and gx equal to -1. So always this product fg is equal to -1 for all x either rational or irrational when x belongs to the closed interval 0, 1. Since fx is a constant function on this closed interval 0, 1, it is R integrable, that is Riemann integrable on the closed interval 0, 1. But f and g are not Riemann integrable functions on the closed interval 0, 1, because this f function this -1 when x is rational and fx equal to 1 when it is irrational, obviously this is not Riemann integrable and gx also not a Riemann integrable. But this product fg is a constant function, so it is Riemann integrable. Next question D. F maps from the closed interval -1 to 1 to R is defined by fx equal to 0 for -1 less than equal to x less than 0 and 1 fx equal to 1, 0 less than equal to x less than equal to 1. Then correct option A is Riemann integrable but does not have primitive on the closed interval 0, 1. Here fx is this, so -1 to 0, this is the 0, and for 0 to 1 fx equal to 1. Clearly f is a bounded function on the closed interval -1 to 1 and f is continuous on this interval -1 to 1 except the point x equal to 0. Hence f is Riemann integrable on the closed interval -1 to 1. Because we have the theorem, this f maps from AB to R, real number R be bounded on the closed interval AB, and f each has a finite number of points of discontinuities in the closed interval AB, then AB is Riemann integrable on the closed interval AB. So by this theorem, we can say AB is Riemann integrable in the closed interval -1 to 1. If possible, G be the primitive of f on the closed interval minus 1 to 1. That means g is primitive. That means integration fx dx equal to gx plus c. That is dx of gx equal to fx. Then gx is called primitive of fx. Then g dash x, that is ddx of gx equal to fx. So fx equal to this 0 when minus 1 less than equal to x less than 0, and fx equal to 1 when 0 less than equal to x less than equal to 1. G is differentiable on the closed interval minus 1 to 1, and g dash minus 1, g dash minus 1 this is equal to g dash minus 1 this is equal to 0, and g dash 1 is equal to 1. So g dash minus 1 not equal to g dash 1. By Darboux theorem, g dash assume every real value lying between g dash minus 1 to g dash 1, that is lying between 0 to 1. But it is not true for this case, hence g does not exist, because here g dash assume every real value, but g dash only takes the values these 0 and 1 only. So not the every value from between 0 and 1. Hence f has no primitive on the closed interval minus 1 to 1, although f is Riemann integrable on the closed interval minus 1 to 1. Question E, improper integral 1 to infinity x to the power n minus 1 by x plus 1 dx converges. Correct option is 2, n is less than 1. Let fx equals to x to the power n minus 1 by x plus 1. Now x to the power 2 minus n into fx. So this is equal to x by x plus 1. So divide numerator and denominator by x. So 1 by 1 plus 1 by x. This tends to 1 as x tends to infinity. So the given integral converges when mu means 2 minus n greater than 1, that is n is less than 1 by mu test. What is the mu test? Let a maps from this interval a to infinity to set of real numbers r be such that fx is greater than 0 for all x greater than equal to a greater than 0, and limit x tends to infinity x to the power mu fx equal to L. Then integration a to infinity fx dx is convergent for mu greater than 1 and divergent for mu less than equal to 1 when L not equal to 0. And number 2, integration a to infinity fx dx is convergent for mu greater than 1 when L equal to 0. And number 3, integration a to infinity fx dx divergent for mu less than equal to 1 when L equal to plus infinity. So clearly n is less than 1 is the correct option 2. Next question, F. Improper integral minus infinity to infinity integration e to the power minus x dx is equal to correct option 2 root over pi. And this is the first we check this whether this improper integral converged or not. So this 1 to infinity e to the power minus x square dx, and this e to the power minus x square is less than 1 by x square for all x greater than equal to 1, and this integration 1 to infinity dx by x square is convergent because by this mu test this convergent when mu greater than 1 and diverges for mu less than equal to 1. Hence by comparison test integration 1 to infinity e to the power minus x square dx is convergent. What is the comparison test? F and g both integrable function on the closed interval a capital X for all x greater than a, and 0 less than fx less than equal to kgx for all x greater than equal to a and k greater than 0. Then integration a to infinity gx dx is convergent. This integration convergent. If this convergent, this implies this integration a to infinity fx dx is also convergent. And if integration a to infinity fx dx divergent, then this implies integration a to infinity gx dx also divergent. So obviously hence this 1 by x square is convergent for mu equal to 2 greater than 1, So obviously this is convergent. So obviously this integration 1 to infinity e to the power minus x square dx is also convergent. Now 0 to 1 e to the power minus x square is a proper integral from 0 to 1. So obviously 0 to infinity e to the power minus x square dx is convergent. Now minus infinity to infinity 0 e to the power minus x square dx, taking limit a tends to infinity minus a to 0 integration e to the power minus x square dx, and taking x equal to minus z, so limit a tends to infinity integration 0 to a e to the power minus z square dz. So integration 0 to infinity to the power minus x square dx is also convergent by the previous result. So integration minus infinity to infinity e to the power minus x square dx is convergent. Now 0 to infinity e to the power minus x square dx equals to 0 to infinity e to the power minus z half z to the power minus half dz. Put x square equal to z here. So x equal to z to the power half and dx equal to half z to the power minus half dz. So we can write half integration 0 to infinity to the power minus z to the power half minus 1 dz. This is equal to half gamma half. This is the gamma function. So this is gamma half, and this gamma half equal to root pi. So we can put here root pi by 2. So minus infinity to infinity to the power minus x square dx, this is equal to 2 into 0 to infinity e to the power minus x square dx. This is the even function, this. So 2 into this, so root pi. Actually this is the question marks is 2. So for proper answer 1 mark, and for justification 1 mark. So for justification you just write this minus infinity to the power minus x square dx is convergent, and calculate this value root pi from this. Next question, G. Let f and x, this sequence of functions x to the power n for each n belongs to natural number n. Then this sequence fn is uniformly convergent on the correct option is 4. For each n belongs to the natural number n, fn x equal to x to the power n when x belongs to this closed interval 0 to 1, and then the convergence of the sequence fn is not uniform on the closed interval 0 1, but the convergence is uniform on the interval closed interval 0 to a, where 0 less than a less than 1. This is the theorem. So the correct option is 4, this semi-closed interval 0 to 3 by 5 less than 1. For proof of this theorem, we choose x equal to 1, limit and distribute fx and x equal to 1, or 0 less than equal to x less than 1. Not necessary to prove this for MCQ, and this limit intends to infinity fn x equal to 0. Therefore fn x is pointwise convergent on 0 1 to f, where fx is the 0 when 0 less than equal to x less than 1, and fx equal to 1 when x equal to 1. Choose a very small positive quantity epsilon, and for 0 less than x less than 1, modulus of fn x minus fx is equal to x to the power n less than epsilon if x to the power n less than epsilon. That is if 1 by x to the power n greater than 1 by epsilon. That is if taking log on both sides. So n log to the base e 1 by x greater than log 1 by epsilon to the base e. Hence n is greater than log 1 by epsilon divided by log 1 by x to the base e, both. Let k equal to, this is the box function, this is the greatest integer function, plus 1. Then for all x belongs to the closed open interval 0 1, modulus of fn x minus fx is less than epsilon for all n greater than equal to k, where k is the box function log 1 by epsilon by log of 1 plus x plus 1. And this k depends on the epsilon as well as x also. So this k is not unique, not single k belongs to the natural number. This k for all x belongs to the closed interval. So convergence of this sequence of functions is not uniform in the closed interval 0 1. Let 0 less than a less than 1, then x belongs to this semi-closed interval 0 to a is closed. This implies 0 less than x less than equal to a less than 1. This implies 1 by x greater than equal to 1 by a greater than 1. This implies log of 1 by x to the base e greater than equal to log of 1 by a to the base e. This implies 1 by log of 1 by x e less than equal to 1 by log 1 by a to the base e. Let k dash equal to the box function this plus 1, the greatest integer function, for all x belongs to the closed interval 0 to a. This modulus of fn x minus fx is less than epsilon for all n greater than equal to k dash. And k dash depends on epsilon only. Sorry, this is x, not x, this is a. This is a. No x here, a is constant here. So this is not x, the log of 1 by x to the base e. So k dash depends on epsilon. Epsilon is variable, arbitrarily chosen, positive small quantity. Hence, this sequence of functions fn is convergent uniformly on this closed interval 0a, where 0 less than a less than 1. But it is not necessary to prove this proof for 2 marks MCQ. Next question, H. This series summation n equal to 1 to infinity 1 by n square plus n cube x to the power 4 is, correct option is uniformly convergent and absolutely convergent on the set of real numbers R. Let un x equal to 1 by n square plus n cube x to the power 4, x belongs to the set of real numbers R. Modulus of un x obviously less than 1 by n square. This is equal to mn say for all x belongs to the set of real numbers R. Now, summation n equal to 1 to infinity mn, this is equal to summation n equal to 1 to infinity 1 by n square, which is convergent as it is a p series with p equal to 2 greater than 1. This is 1 by n square, so this is convergence series by a p series. Hence, by Weierstrass M-test, the series converges uniformly and absolutely for all x belongs to R. What is the Weierstrass M-test? Let A is subset of R and Fn maps A to R be a function for all n belongs to natural number n, then sequence Mn be a sequence of positive real numbers such that modulus of Fn x is less than Mn for all x belongs to A and for all n belongs to natural number n. Then the series summation n equal to 1 to infinity Fn x converges uniformly and absolutely on A if the series summation n equal to 1 to infinity Mn is convergent. This is the Weierstrass M-test. Next question, I. The radius of convergence of the summation of series summation n equal to 1 to infinity twice n factorial x to the power n by n factorial square is, the correct option is 3. Let n equal to twice n factorial by n factorial square, then the given series is summation n equal to 1 to infinity an xn x to the power n. Then an plus 1 equal to 2 into n plus 1 factorial by n plus 1 factorial square. Then an plus 1 by n, this is equal to 2n plus 2 factorial by n plus 1 factorial square into n factorial square by twice n factorial. So 2n plus 2 factorial can be written as twice n factorial, twice n plus 1, twice n plus 2. And n factorial, this n factorial in n factorial. And this n plus 1 factorial square, so n factorial into n plus 1, n factorial into n plus 1. And cancel this n factorial from numerator and denominator and twice n factorial from numerator and denominator, and we get this. So 2 plus 1 by n, 2 plus 2 by n, 1 plus 1 by n, 1 plus 1 by n. And when limit n tends to infinity, modulus of an plus 1 by n, so this equals to 4. Hence the radius of convergence R equal to 1 by limit n tends to infinity, modulus of an plus 1 by n, so 1 by 4 is the required answer. Question J. If a0 by 2 plus summation n equal to 1 to infinity bracket a n cos n x plus b n sin n x is a Fourier series of the function x sin x in the closed interval minus pi to pi. Then identify the incorrect statement. Actually, this is the incorrect statement is 1. This series converges to x sin x in the closed interval minus pi to pi. We cannot say this because